free bits enables the work module to learn without tuning and scaling down large returns without. When we have a sparse module, sparse environment, sparse reward, we can get return a big reward, but this action will not lead to solving core problems, and basically you get stuck in the, so they don't scaling the large rewards. For this they use here. This is will be used to scale loss can lead to divergence where absolute and Hiver losses stagnate learning. Nothing that they have told them. We suggest teamwork predictions as a simple solution to this dilemma. Format the version of the target Y. To learn the prediction to the network, we apply the best transformation. Basically, they're using neural network to simulate this. The neural network is differentiable, so they're using that.
What they're doing there is really compressing the range. It's very similar to perceptual and compression in audio, and integrator windup. Basically, you load the error in so much that it blows things up. This is a nice technique because the compression of the dynamic range essentially changes the problem from a arithmetic scale to a decibel scale, and it means that you don't have to change inputs and effectors. You still wind up with about something that the system can handle.
Thank you, Asterix Cat, for the notes here, for the information. We use similar predictions from the decoder, the word, and the critic, basically almost everywhere. It also switches input to the encoder using the similar function. Especially as it's just state, with similar predictions, there is no need for communication culture rewards, introducing non-stationary flow reward normalization, or adjusting neural to threats when new extreme values are deporting learning work model learning. Basically, this is the step at which brings the step at which the model learns the gist of the ropes of the world, how the world works, which actions will lead to each result, and so on and so forth. The work model learns compact representation to the same here without the encoder. The decoder is not used here to best of my knowledge the actual critical learning. It is used just as a representation to reconstruct not only by combining the context layer here with the hidden layer here. You can see this one here. Cap etc. XT. We implement the work module's recurrent state space model. Recurrent because it's using this hidden states here. State space because it knows the state of the world, as shown in figure 3. First, the encoder maps the sensory input to the stochastic representation. The sequence of this representation given past actions are I minus T1. A is the actions. The concatenation of HT and ZT forms the module state from which we predict the reward FT, and episode continuation parts with CT. Basically, this CT tells us should we explore further, or we should cut the process but do not explore in branches. And we could take the input to ensure informative representation. That's why this is the up encoder part of this architecture. Figure 5 visualizes optimal variable prediction of the rows. The encoder and the decoder use convolutional neural networks. for visual interpretation of multi-layer perception for word information representation. The reward anti-simultaneous producers are also of software distribution that we take straight to games through the sampling step. Basically, we're using a softmax. We're using softmax also for action selection, if I remember correctly. We can see here that this is the input, the input, and here we have the inner state of the model, how they predict it. This one here is not quite as the model one here, but I think we need to improve only the opening color in order to get this right. Also here, and here, and here. Not quite correct, but let's go on. Model parameters are optimized end-to-end to minimize the prediction cost, the dynamic costs, and the representation loss. Better be representation. Here we can see the final loss here. The prediction was trends of the color and the water prediction where in what loss and the continuum prediction where finale classification was. This is this one here.
Now, I might be wrong, but I think this is how the critic is actually influencing the rest of the system, is through that prediction loss. Is the critic is really making the predictions for reward and for what they call continue.
For training aerodynamic representation is basically training, let me choose one of the colors. These two here in both directions, depending on the which one we have stop gradients.
Quick question. So in figure 3,
Okay, do we have one more?
up in figure 3, because it says it looks like it's generated from the the last hidden state, and then
Yes,
an action,
it is
and
here.
then z sub whatever.
Yes,
But
basically we're using this neural network here. The zeta state, the context output under action.
Yeah, that is just an MLP in that position.
Yes.
I'm
Yes.
just mostly wondering how they trained it. Like, what's
Uh,
it?
Let me see where is it. Isn't this this function here?
Yeah, as far as I can tell, that's what drives the whole system is this loss function and the backprop through the various neural networks is how it actually trains. Or are you talking about what it's kind of complicated and they do training at every time interval and then accumulated training over long time periods, and then there's the loss functions are kind of complicated.
Get the labels to train that MLP.
We don't have levels here, we have a target.
Could you say that one more time?
Me or the other guy?
You.
I think that we don't have levels here, we have a target. Only one target here. One level if you want to say it that way. Everything.
Yeah, it does get information about rewards, and there are times when it's trying to use the critic to predict the rewards. So when it doesn't get rewards directly, the critic is trying to give an indication to the rest of the system how much it expects it will be rewarded. and those are the two things that drive this. And then it's got this other chunk called the continue, which I don't entirely understand. There's an equation for it, and it does something. It's basically imitating some parameters that I think that it would normally receive from the environment, but I'm not sure.
Isn't continue the continue signal basically, which is
The branches from the space, from the exploration space, so we don't explode.
Yeah. So, like, I don't know, you fell down the ravine. And in the simulator, you would ordinarily not have that. So you train a neural network that tries to predict this stop signal. Or continue signal, like, however you want to frame it.
Okay. The deny contains the sequence module to predict the next representation by minimizing the chaotic values between the predictor and the next representation. The representation turns the representation to become more predictable if the deny cannot predict the denies cannot predict the distribution or increase to factorize the next prediction for sampling when training that critic, actual critic. Here is something fixing. The two losses differ in the stop gradient operator, and there was scale. Basically, which one of these two is it? Which is here? Let me erase something. Okay, basically, when we have to stop it again here,
The right-hand side there, where it says actor-critic learning, is that whole thing the actor-critic, or is that a representation of what the actor network is, and then another one for what the critic network is? The only thing I saw for actual critic feedback is equations, not in these diagrams.
okay.
So,
So yes,
we need to quickly jump in with the actor critic. The actor critic is just the method of learning they're using in, like, in this case, a simulated environment. And you match the values. So the value function here is literally just to reduce the variance of the, like, actual rollouts, just like a normal reinforcement learning.
Yeah, to me, actor-critic is just a particular factorization of the of that mechanism.
okay. So, what was pure? In color. Okay. This one here allows to train in this the encoder, and the we are creating the deny predictor. Basically, like so. We are creating this part in order to train in this direction. Basically, visual complex to the environment. Complex to the environment contains detail necessary control, and this prompt does not realization requires to simplify the representation, make them more predictable. In 3D games, the background is often static, and individual pixels may matter for the task, requiring a weak equalizer to perceive fine details. We find that combining 3 bits with small scale the representation was resolve this dilemma, allowing for hyperparameter perfected hyperparameters across the domains. Needs.
Well, hyperparameters are like training technology.
Anybody have an idea? Okay.
They are explained above there something, to avoid if you go above the equation 5. So
Yes,
you have to avoid. Yeah, here.
Needs. 27. Okay, I have to look at that.
Yeah, I believe I remember this was something in the Dreamer V2 paper. They also did that there, which I think is just effectively like a regularization mechanism.
Yes. The occasion observed spikes in the keyword process in earlier experience, specifically with the reports for give directionality in colors. To prevent this, we parameterize the categorical distribution of the encoder and the line predictor as mixtures of 1 uniform and 1% uniform and 9% neural network output by regularization. Formal address and time experiments are summarized with W1.
Free bits, which I think I understood, but it sounds like a free bit is just a dead point in the gradient. Is that right? That basically, if the gradient is smaller than a certain value, you set the gradient to 0. This is like the second.
This disables them while the audience members to focus on the work module on potential prediction loss.
Yeah,
So
it
one
sounded to me like if the gradient is small enough, it says, well, this is probably just noise, so I'm going to set the gradient to 0 and see how things go from here.
Yes, maybe as well be.
But it's referring specifically to those other losses, right? So it's kind of like once it's learned to do those parts well, they turn it off.
It's not exactly the same as turning it off, but it's being selective about when you learn that if there's a sudden change in the gradient, it's clearly not being successful right now, so I need to start learning in this direction. I think that's what it's doing, but
It's clipping them.
well, it clips, but it also has like a dead zone in the middle, and the dead zone is so on the. Just imagine a 1-to-1 gradient, and clipping would be flattening that out at the outer extreme. I think that's what that is they're adding a dead zone. Anyway.
Yeah, so if you dive into the paper that introduced the free bits, wait a second, I can just link it. So the object is more or less that you put a constraint on the thing, on the latent, that there's a minimum amount of information per group of the latent variables. So it has something to do with how exactly they put they condition the latent space. It's some form of regularization.
So it's designed to structure the latent space, is what you're saying.
Yeah.
Got it. Thank you.
Just above that, if you go, just below the equation 4, below the equation 4, I'm still trying to get my head around that sentence where it says that, so basically if we start from the dynamics, loss trains the sequence model, just below the cursor. Yep, so just starting from there, I'm just trying to understand how all these losses, like what they're really influencing.
What they're interesting?
Sorry?
Can you repeat your last sentence?
I'm just trying to understand what these losses really influencing. What are they trying to do here? So there must be, but in here, this is more like is a posterior and is so stochastic representation. Where this stochastic representation is coming from? The the distribution over Z conditioned on H and X.
The distribution over the
Yeah, there.
yeah, about this.
Yep.
Okay, let me go a little bit up. It is the encoder.
Yeah.
Okay.
So this has to do with kind of the mathematics behind the VAE that effectively, yeah, it has to do with the stochastic variation inference framework you put into VAEs, but essentially the idea is you have one. So effectively what you're now trying to do when you actually sample in that space, you are just using the encoder, you're computing the expectation over the encoder to kind of get a faithful estimate of how the Z's look like. It's about the dynamics, the decoder, etc.
Yeah, but here we in VAs there's an assumption on Z's, isn't it? There's normally Gaussian prior that is used. So in this case, the what is this assumption? What is the prior that is used?
Yeah,
It's one hot.
Exactly. And this is also where these free bits come in. And kind of what the free bits do is think about it, yeah, exactly like in the visualization. So you have like a grid, and every single row you can think about it as like a group of latent code, additional structure.
Understand. Oh, sorry. I probably missed this VQVA. So, but there's additional constraint. Where we were reading that sentence. Then they talk about the representation loss. After that, I think was
Autoencoder.
Yeah.
What's this?
5, they are just looking at the probability of getting a certain C under the Q representation. Remember, the Q was the encoder. Assuming the P is fixed. So effectively, you have to.
This one question here, right?
Yeah. It should be that one, isn't it? So, yeah.
So what they are now doing is they're doing something slightly weird, but it's probably because of their framework. Is they're setting a maximum of 1. Well, though it could also be because of the it's a maximum. So this max is due to the what's its name? Free bits. So they just happen. So usually it's a hyperparameter where you say that you have like lambda nats at least per subset, and here they just say you have 1 nat per subset.
Are you sure these are for we were talking about subsets of the one hot, or are these just like loss values? Like K, I understand here is this is a threshold for the dynamic loss and the representation loss for them to be disabled.
They are looking at kind of different elements of a grid. It might be that the way they're defining the C is they just say, well, we have one huge group. So we don't have K groups, we have one big group. And we use that to set the minimum. But usually what you do is you set a minimum across every single one of those groups. And then you say, well, the actual loss is the maximum of either lambda, so kind of that's your lower bound, or no, that's your upper bound, and the KL divert group, then this would kind of regress to this representation.
How being represented in declaration there that's actually doing that? That doesn't seem.
Yeah.
It is? Okay.
So in other words, normally like KL divergence just tell us the difference between, isn't it, the match between the distribution. So here what we're saying is that they expect or they are constraining that difference to be at least 1 because of those free bits you just explained.
At least a little bit more than 1. It's 1 nat's bigger than one bit.
It is 1.4.
Yeah.
Yeah.
Okay. Thank you.
Okay, let's continue with the actor critical learning. Doctor and critical neural networks run the first further on the abstract sequence predicted by the work model. So now, during environment interaction, we select actions by setting for the actor network without looking at one. Doctor and critic operate on model states, which is basically HT and ZT, which is basically these two alone. And this benefit from Markovian representation warned by the work model. Vector aims to maximize the expectation return, which is equal to 0.997 for each model state. To consider errors beyond the representation horizon T(x)16, the critical errors to predict the return of each state at the actor behavior. And these are the formulas for the actor and critic. Here, I think this is the expectation. We have, and here we have the state. P theta, I think it is the neural network that returns what is the next action. Starting for representation of referred units, the dynamic predictor and actor produce a sequence of image model states, actions, rewards, and continuous paths. To estimate returns that consider reward beyond the predicted horizon, we compute bootstrapped alpha returns that integrate the predicted rewards.
PD lambda approach?
It's exactly that.
Okay, thank you.
So it looks a little bit different here, the trade-off between the true returns, which you can get easily here because you have a simulator, and whatever the value predicts, which, yeah, it's always questionable, in my opinion, to have the value network in model-based systems anyways, but it tends to reduce the variance a little bit. And the kind of the equation 7 is exactly what I talked about previously, with the C effectively just, if Z is 0, you continue flag, then you're just not going to kind of consider the future, because there is no future. You ran into a wall.
I got that. Okay, thank you.
Alpha returns beyond where a pair of possible predictors, one of the critic predicts expected value of potentially weak. We choose a discrete regression approach for learning the critic by fitting this in two product targets. Basically, this is when we have a bucket. This is about the two product bucket 1, 2. Some number, let's say 0.5. It goes to bucket 1. If we have 0.7, again goes to bucket 1. If we have 2, goes to because these are on ranges, let's say from 0 to 1.5, it will go to bucket 1. And from 1.5 to 2.5, it will go to bucket 2. That let the critic maintain and refine a solution over potential returns. So this the transform returns using the system-based buckets BI. The Cubic network outputs a softmax distribution over the buckets and outputs is found as expected bucket value under this distribution. Importantly, the critic can predict any continuous value in the interval because the expected bucket value can go between the buckets. To train the critic, we insist to transform the target and then return to particle that each of them is the soft label. If connect to these values, it produces a vector length B where our elements are zero except for the two entries that pass to the encoded continuous number and position key and key 1, key plus 1. These two entries sum up to 1 with more work to give to the entry that is closer to the encoder number. Basically, if you have, again, to begin brackets, if we have a continuous line here, and we have integers, let's say 1, 2, 3, 4, 5, and so on. And let's say we have something at 3.3 as a value, we will get, let's say here, 0.743 and 0.34544.
They place their in doing this kind of trick for interpolating between bins. Every place else, like with actions, it's a softmax. Is that not true? And there's a single weld of possibilities that come out of the set. You have probabilities associated with each of those actions, but you only take one action. You never. What's going on here?
Yes, I think so.
Thank you.
It's usually the reason you do that for critics is to get more or less accuracy in like these different ranges. But it's still like you're summing over potentially very, very long chains. So it can happen that you have gigantic ranges while simultaneously also needing a decent amount of accuracy, because like the difference between two different states, if you compute the advantage, might be very, very small.
Right.
So one of the tricks you could do.
Very infrequent rewards, for instance, that might show up with this kind of thing, or reinforcement that might show up with this sort of thing. So the percentage of actually learning over those rare times when you don't get a reward.
Yeah. So, and the reason you do this 2-hot encoding, or also sometimes 1-hot encoding, is to get just more accuracy. You can also see that if you look at, for example, the Rainbow paper. People also do this for QLEARN. Effectively, just do like a linearization of the space, where in which
Okay. Given two hot decoded targets, YT equals stop graded to hot teamwork R loss for classification of soft targets. This is the loss for the critic. Basically, here's the YT. We found the discrete regression for the critic to accelerate learning, especially in the same discrete regression approach for the word prediction of the word modules. After learning, network allows to choose actions that is by ensuring sufficient exploration through an entropy regularizer. While the scale of these results are heavily depends on the scale and frequency of the words of the environment, which has been changed for purest algorithms. No sacrificing current performance under these dense returns. To stabilize the scale of returns, we normalize them using moving statistics. This is IMA, moving average, right?
yeah, it's not only average. You also have like moving standard deviations and stuff like that.
Okay. For task with the dense rewards, one can simply divide items by the standard deviation, similar to our previous work. While when rewards are sparse, the dense standard deviation generates more, and this approach would amplify the noise contained near the renders, resulting in overly deterministic policy that fast exploits. The weakness is therefore by doing things by the scale S with the discussed multiple choice law. Oh no, it is not. Oh my bad. One is where they need to accept a minimum choice of 1. This simple change is the key to all the people and roughly scale and across this as far as the rocks. Before Dreamer between selecting the grading in the first term by source ticket surpassed the second term is completed in the closed form. The Mexican environment refined that normalizing contains by the exponentially became the all players and were actually just caused by a small number of particularly easy result running from already this while being reduced to such opponents with scale tests by exponentially decaying coverage of the large range from the 5 to 8. This is equivalent to an affinitive transformation that maps these returns. This is respect to one zero function expectation version that this part works without sacrificing final performance under these networks using fixed temper scale. And the implementation details. The utility of DNV2 across diverse domains with over 150 tasks under fixed habits designed to best at hand. Moreover, we apply DNV2 to the change your performance of the stochastic change policy and avoid competitive version errors. This is the deterministic policy widely used across the research apps. The source code and the medical results are available on the project website. And I can now read. 1 second, please.
Yeah.
Okay. Here, we have a simple example. It's called GPU version of JAX. This is the pip freeze of the environment. They're using they are not using PyTorch, they're using TensorFlow, which is strange, but okay. We have several hyperparameters here, I think. And if we run this, let's wait a little bit. Here we're speaking about 5 gigabytes of memory. 32% of my NVIDIA 4090, which is good compared to the other models that we have discussed in this stream. Okay. I have problems with running the training with other for and here are the different benchmarks, I think. And not different results of the different losses. Just like this example, score, reward, rate, action max, action mean, and different trends that I don't know the mean exactly of. Okay. We can see here the module size. The largest variant is 2 million parameters. As I have shown you, it can be run on the low-end GPU right now. A GPU that can run this cost GPU 4060. Equalizers, the force equalizer, and different types of tricks that they're using here to improve the previous architecture. Here we have different explains to the environments. Last year we had the stream about this, but we haven't even had a discussion about the paper. 1 second. No, I cannot find demo of this agent. But I can find the Yannick's paper about Dreamer, Yannick's video about Dreamer V2 from 3 years ago. Okay, that's it for me.
Well, it was certainly interesting. There is so much in the appendices on this. It's overwhelming, quite frankly.
Yes, I felt the same. And I wanted to learn more about the things that I don't understand.
Yeah, this was nice. I'm glad you brought this paper up. It's a very interesting one. I was kind of curious about the community response. Anyone can say anything to that end?
It's,
Yes?
so in my experience / opinion, it's not that great. Not because it doesn't work, but because of what you have to do. If you actually get them to run, they are very efficient. They can do things that other methods can't. The problem is, by the time you finish tuning them, you might as well have run like something like PPO for just twice the length, and you are still going. Universal choices only work for these Atari or Minecraft-like problems, and in general, we don't want to play either Minecraft or Atari.
Isn't that the point of this paper, though, that they didn't have to monkey with the hyperparameters to get it to work over a lot?
But these are still very, very similar. So, for example, just the fact that both of them are visual change a lot of things. Like, they also have the proprioception stuff, but for the proprioception stuff, you have the problem that you don't need such a model to actually make progress. There are just so many. Take it, you're going to put it onto your problem, which presumably has some very, very strange underlying things in their dynamics, because otherwise it would have been solved already. And then you have this huge thing, it doesn't work. You don't know what to change, because it's just so huge and so...
The Python environment, say, print your work.
That's all it's set up for. It only has a visual encoder.
I mean, you can also do proprioception. And I'm not only meaning... I don't only mean like visual stuff, like stuff which is very game-like, which is hard to put into words, but the actual problem of, for example, driving a cart around a production facility is very, very different from doing something kind of similar in an Atari environment. So, for instance, you don't have to deal at a certain speed, then, like, the real-world car is going to try, and it may or may not succeed, but it's entirely different from like a simulator where you just say you go that speed and then you go that speed. And you can do things now with like these random. There's just so many things to tune, and it's not stable enough that you can. And the parameters you have to set are not interpretable enough that you can say, well, the reason this doesn't work is specifically because make this work. You can definitely make this work. You can. It's especially Dreamer is rather efficient. MCTS isn't, but Dreamer is rather efficient. It's relatively sample efficient, but it's only sample efficient once it's tuned. And that gives you that kind of catch-22, which is when you go out and you try to collect experiences, then by the time you have enough data to actually make it hit the efficiency targets that they are boasting, you might as well have trained a different algorithm.